Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Ellyn Baines with us today. Hello, Ellyn.
Hello.
How are you today?
Oh, fine, fine. Just keep on keeping on, you know?
And what is this? It is June 24th, 2025 as
Mhm.
we record this. And so we are past solstice. And Phoenix is, of course, quite definitely in its hot moments here. So yeah, we're up over, what did we hit? 110 the other day? I think we're only
Oh,
yesterday. So it's doing fine.
yeah,
So in
yeah.
Phoenix, early in those deserts, you learn how to get up early and do whatever you got to do in the morning, and then you get out. So, and Ellyn, what is your geolocation?
I am in Virginia, just a bit west of Washington, D.C., where I work.
And humidity up yet in the summer?
Oh, well, for a while it was rainy and cool, and now it's hot and dry. So we always have something to bellyache about
What?
around here.
Well, it must be good sometimes. Fall is pretty
Yeah,
nice.
yeah,
Fall is
it is nice. Yep.
very cool. And Ellyn, what do you like to do for research?
I like to use telescope arrays to measure fundamental parameters of stars like size and temperature.
That
That
is
is what I'll be
awesome.
talking about today.
That is very cool. That was short and sweet. And that is going to bring us to this very awesome AJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. Vintage NPOI. New and updated angular diameters for 145 stars. And Ellyn, take us away.
Very good. I would like to do what many do when we start and acknowledge my co-authors here, my collaborators. They're the people who keep the lights on and the bugs out and kick whatever needs to be kicked whenever it needs to be kicked, and they know where to kick it.
Good.
But of course, this is just a small part of the group who have been involved with the NPOI
Mhm.
throughout the years. So I definitely want to tip my hat to the folks who have worked, on the instrument previous to design it, build it, operate it, upgrade it, repair it, all those things,
All those
so
good.
that we can do our thing.
Very cool.
Okay,
Good
yeah,
job.
yeah. So I'm going to go a little out of order of the paper. I'd like to start with the instrument. So that's kind of section 2 if you want to look at any
Absolutely.
text
Let's
there.
slide in. Go to,
But
I'll get there quickly. There we go. NPI.
yeah, the NPOI is the Navy Precision Optical Interferometer. It's located on Anderson Mesa near Flagstaff, Arizona, so closer to you than it is to me.
Yes.
Um, but a beautiful part of the state. I just love going up there.
Nice.
We observe across a wave of optical wavelengths, about 550 to 860 nanometers, 16 channels through that
Okay.
range.
Okay.
We observe using 2 to 6 telescopes at a time. Most of the time, we're 3 to 5 telescopes. So, 2 is when we don't have anything else, we can do that. But 6 is very awesome, but hard to do. So we kind of spend the time in the middle. And I
Mhm.
will note that I call them telescopes. We technically use siderostats because the mirrors are flat instead of being curved. But
Mhm.
we know what telescopes are. People are more familiar with the term. So just forgive my vocabulary
No, no,
if
it's very cool. People should learn
yeah,
the term. It's very cool.
yeah, we like the word telescope. So we can resolve things down to about 1 milliarc second, which is
Okay.
about the size of a quarter seen in California from New York.
Nice.
And
Good.
it's like,
It's
I think I
amazing.
calculated it was like 30 micro degrees. I mean, these are
It's
very,
amazing.
very fine resolution. And we can get lower than that. We've measured stars that were smaller than that, but the data get correspondingly hairy and higher error. So we sort of use that sparingly.
Okay.
If there's something of particular interest, we'll go after it. But about 1 milliarc second to about 8 to 10 milliarc seconds is really our happy range of measuring the
Nice.
stars as I measure them.
Nice.
Okay. So
Cool.
the endpoint has been in operation since 1996.
Hmm.
In the first handful of years, from 96 to about mid 2002, it operated in a slightly different way. We used 3 spectrographs, 32 channels, and a slightly wider wavelength range. We went down to 430 instead
Okay.
of 550.
Okay.
Um, and this will become important later, but back in the day, things like data saving and data transfer were real problems.
Yes.
It's not
Yes.
something we have to think about so much now, but they were an issue. So we went down to 2 spectrographs instead of 3, 16 channels instead of the 32, and we knocked that bottom 100 nanometers off of the short range, which ended up not really being a big deal because our system is quite insensitive to those shorter wavelengths. So
Okay.
it didn't affect many of the targets that we would be observing anyway. So
Okay.
that was good.
Nice.
Let's
Very
see.
nice.
Yeah. And since 2002, we've been observing pretty much the same way. So it's a large, fairly homogeneous data set.
Yeah.
And
Longitudinal coverage too.
yeah. So I started NRL in about 2008. And I was as a postdoc, focused on my own projects, exoplanet host stars, K-giant stars, things like this.
Yes.
But as I was sort of getting familiar with the NPOI and looking at all of the wonderful things that it's done, it's a great binary star machine.
Oh yeah.
Stars with disks, rapid rotators, oblate stars, asymmetries, all that sort of thing. My sort of wheelhouse is the angular diameters of these stars. So what is the size of these stars to us? All right, how big of an angle do they take up in the night sky? The sun is very big, but farther away. The moon is much smaller, but much closer, and they're about the same angular size in our sky. So that's what we're looking at.
About 400.
So about 10 years ago, I was really looking at the data archive, realized there were a lot of stars that weren't published. And this had to do with people working on long-term projects, totally understandable. But I started talking to these people like, do you think maybe it's time to start getting some of these stars out and published? I mean, this could be useful for the community. And they were very, very nice about it and said, oh, yes, that sounds great. Let's work on this together.
Cool.
And then some retirements started to happen. So more and more data sort of landed in my lap. And this led to an 87-star paper of new and archival diameter measurements.
Okay.
And I thought, that's great. That's a huge sample. That was the biggest single sample size in interferometry, optical infrared interferometry at the time. I'm like, my job here is done. It's all good, right? It was not.
No.
The pandemic hit, and we weren't really observing because nobody was open. So I started looking some more and got 44 more angular diameters, some new data, a lot of archival data, and thought, well, that's definitely it. We're done here. Was wrong again. And so our third big paper was 33 stars.
Okay.
Not even this one yet.
Right.
And by the end of that one, thought, all right, that's definitely it. There's nothing else to be doing with the data archive. So much so that I published a huge table in an SBIE paper of all the stars that we've observed with the NPOI through the years.
Okay.
When it was observed, how many observations, and that was in an effort to bring collaborations. If you have a star of interest, please come talk to us.
Yeah.
We'll see if we have anything usable for that. Just trying to get the information out there, what was in our data archive. What I eventually realized, and that brings us to this paper, we are getting there,
All good.
that we either had data from the late 90s, early 2000s, or from 2002 on. And there weren't any data sets that really combined those two, and I wondered why. And that had to do with conflicting data structures.
Right, yes.
So our programs could do one or the other, but when you tried to ingest them both into the program I was using, it just went, I don't know how to deal with this, which I don't blame it. So I just wrote a program that could take the results from the earlier data, take the results from the later data, do a global diameter fit, and went from there.
Cool. Very cool.
Right. Yeah. So that presented this paper, 145 new and updated diameters. So some of these have not been published by the NPOI before.
Beautiful.
Some have, and they just have, here's some more data. And those are indicated in the tables if it's been published before or not. So it's pretty easy to find.
Okay. Very
So
good.
when you add up this 145 stars with stars from the previous papers, that's about 240 targets, which is a really good size for an interferometric sample size. So what interesting things can we start to do with a sample of this size and a wide range of stars? We weren't just studying, cool stars or hot stars or anything like that. It's just what was in there. What can we observe? What have people done for the last almost 30 years?
But you got a whole zoology of different types of stars.
Yeah.
Oscillators, a little bit.
Yeah. So diameters, now I'm going to get into sort of the beginning of the paper here. Diameters are important because they are direct measurements from interferometry. We're not making any assumptions about stellar structure or the properties of the star, or the evolutionary state.
Right.
How big does it look to us? That is what we are measuring. These measurements are foundational to astrophysics. Sort of a lot is built on fundamental parameters of stars. So the more we know about that base, the better when it comes to extrapolating that to other things.
Yes.
It tells us about the stars and their environment. So if there's an exoplanet host star, you can now determine the habitable zone with some precision because you know the temperature of the star.
Yes.
Are there binary companions that you might not otherwise know about other disks that haven't been well characterized. So we can start to look into all of these things.
Hmm.
And we also need benchmark stars for large surveys like Gaia or Apogee, because, you know, and for stellar models. What does the model say the answer is going to be for this star? What do
Definitely.
we actually measure? And do they match? You know, and which
Want me to
stars
answer
work?
that?
Which models work best for which kind of stars? Because there's a lot of stars we can't measure with interferometry. So
Right.
when we have some confidence in a given model for a given kind of star, then that, you know, can lead to more confidence for applying that to other targets.
Absolutely.
So there's lots of tables here. None of them are particularly interesting to look at. That's where all the science is. I mean, if you're interested in the science of this,
You gotta
the
have the
papers
numbers. You gotta have the
are,
numbers.
are where it is. And I will note that several of the papers are shortened here because they're very long. They're 145 stars. The observing log is well over 1,000 lines. They didn't want to publish that on the, you know, in the journal. So know that you'll see the tables, but if you want all the information, just go to the online version and you can get all of
It's
that
all
there.
there. That makes for a nice, tidy PDF version of the article.
Yeah, because otherwise it's just flipping pages like, okay, yeah, more stars. Oh, look, more stars. Oh my gosh, here's more stars.
You will never hear me object to that.
That's right. Okay, so figure 1.
Yeah, let's okay, where are okay, figure 1 looks like color
Yeah.
magnitude. Yep.
This gives some context to the stars that we've observed. So this is a color magnitude diagram. You have the B minus V color index along the x-axis, the absolute V magnitude on the y-axis. The red squares are stars presented in this paper, and the big black circles are stars presented in previous NPOI papers that are referenced earlier in the paper that I talked about, the 87, 44, and 33 stars.
Okay.
These small points here are from the JMMC Stellar Diameter Catalog, which is a fantastic resource. I use it all the time. And basically, is it north enough for us to see? So north of about minus 10 degrees in declination. And is it bright enough for us to see about 6th magnitude in V or brighter?
Okay.
There's no cutoff for size here.
Okay.
So you can see it's sort of an empirical HR diagram. You can see the main sequence.
Yes.
You can see that we observe a lot of giant stars. And it just puts this in context. And I've actually done the calculations of what percentage of the stellar diameter catalog that we've observed, but I don't have that off the top of my head.
Okay.
If you're interested, you can get in touch with me.
Is there any overlaps between the small black dots and the red squares and larger circles? There are?
Yeah.
Okay.
Yeah, you just all over plotted on top of each other.
Okay.
So,
Okay.
yeah.
So we can get cross correlations going and all of that.
That's right. Yep.
Okay.
And to see how well that catalog does with its diameter estimates.
Very good.
For instance.
Beautiful figure.
Yeah, so figure 2 is our temperature distribution. Our referee recommended this and I like it. So it's there. You can see we observe a lot of cooler stars and sort of mid-range. We don't observe a lot of hot stars, but that's expected with the kind of limitations that we have. So, yeah, any comments on this? Excuse me. Okay. So we're going to scroll down a little bit, talk about data. We're not going to talk about data reduction very much. You can read all about this if you'd like, especially Christian Hummel's papers do a really nice job of explaining how data are collected and processed. We basically average the data points into 1-second averages, and then we can start to fit those. We observe alternately with calibrators and our science target.
Yes.
So our calibrator, we hope, is really, really boring. It's small, so it's unresolved. It's just like a point source in the sky. But we hope that it doesn't have any stellar companions that we don't know about.
Or it's pulsating.
That is pulsating, yep. And I will tell you, I learned that lesson very early on. One of the first stars I ever observed was Upsilon Andromeda, which is a very famous radio velocity planet system, and it's got several planets. And one of the things I was doing in my dissertation was trying to see if a face-on binary could look like a more edge-on planetary system. And we got this beautiful binary signature in our observations of this star. And we were just like, oh, we've done it. We did it. We did it. It was the calibrator. It was not the target. So, yep, we observe with as many calibrators as we can, at least 2 if possible. And we sort of alternate between the calibrator and the science target. So we can say we kind of know what's going on with the calibrator. So we see how the calibrator changes over time, and that can be due to atmospheric effects. just the atmosphere bumping the air around all over the place. Yeah.
Changes. Yep.
Yep. Scintillation. And for instrumental effects, like long-term instrumental effects, is the instrument's cooling or temperature changes or whatever. And we can remove those effects because we know what the calibrator should be doing. We see what it's doing. We can then correct for that. And then we have the calibrated data points. And I'll talk about the data points a little bit because it's
and that
kind of strange and
it's allowing you to go across epochs, right?
Yep. Yeah. Instead of and we observe them as close in time as possible, because if things are, especially for stars that change, you want as close to a snapshot as you can get.
Yep. I'm with you. Cool.
Yeah. So boring calibrators are good. Interesting calibrators we put out in the world because nobody else needs to spend their time with those unless you want to study them scientifically. So interferometry, this is our technique, and this uses multiple telescopes to observe a star at a given time, right? And the advantage is that your resolution now depends on the distance between your telescopes instead of the size of the telescope.
Yes. Yes.
So instead of building one 100 meter, 200 meter, 500 meter telescope, which is very hard and extremely expensive, you build two telescopes that are 100, 200, 500 meters apart.
Yes.
So the resolution is exquisite.
Nice. Beautiful.
The sensitivity is where you take the hit because you've removed an awful lot of glass from that huge, hundred to hundreds of meters telescope.
Right. Yes.
So your resolution is great. Sensitivity, you wish could be better, but you do what you got to do. This is what we have. So you hopefully you can realize. So if I'm observing, just say with two telescopes, we'll go with a simple case.
Okay.
And there's a star that say kind of where this globe is. Okay, let's use that.
Okay.
So you'll see that the star is closer to one telescope than the other. So the light will take slightly longer to get to that telescope.
Yes.
So what we need to do is for the closer telescope is introduce some delay into that because we need this light path length to be exactly equal to this one. And when we bring the light together, that's where fringes appear. Interference fringes, hence interferometry.
Cool. Yep.
Yeah. An annoying word to type every time, but it's okay.
Very good.
Yeah, and there's a couple interesting things about these fringes. So you have the size of the fringe, which is the easy part. That's the amplitude. That's what I use. That's what tells you about the size of the star.
Yes.
You also have the phase, which is where that fringe is in baselines, in basically in space.
Yes.
Where between the two telescopes. And that's very hard because the atmosphere just jumbles that data so quickly. But there's various techniques that can be used, both observational techniques and then post-processing techniques that can pull out some of that phase because that's where a lot of really good information is. Asymmetries show up beautifully there, star spots, oblate stars, things like that. But we're going to be talking about the amplitude here, the size of the fringe. So it's basically comparing the maximum intensity with the minimum intensity.
Okay.
And that is known as the visibility.
Yes.
Okay. So you've got the equation just under your highlighted part there. And we'll go to figure one in a moment. But first, you can see it's not a complicated equation. I don't do complicated equations if I can help it. So J1 is just the Bessel function. It's a mathematical function.
Yep.
X is a stand-in for pi, which we know. B is the baseline, which we also know. And then lambda is the wavelength, which we also know. So we're solving for angular diameter.
Yes, theta.
And that's it. That's it. I say like it's easy to do.
Very cool. Well, especially since you get rid of the squares here and it all just sort of presses down into a simple algebraic expression. So
that's right.
I'll modulate J1, but okay.
Yeah. So we begin with the uniform disk. This is for just if the disk were completely uniformly illuminated, which we know is not true to life.
Right.
The stars don't look like, mirrors. But we can then correct for limb darkening. That's an effect that you see where the edges look a little bit fainter than the center. If you do a search for the sun in visible light, you'll see that every time. And all stars have this limb darkening.
Absolutely.
It just depends on how much.
It's just an atmosphere effect.
Yeah, exactly.
It's a viewing equal atmosphere effect.
Surprisingly hard to measure directly, but we'll get into that a little bit. Here we just use linear limb darkening coefficients, pretty simple, sort of the simplest approximation. Okay, so we can go down to figure 3, I believe.
Okay, 1 second. Okay, so you are using Atlas. Okay, I'm with you.
Oh, yeah.
Do.
Yeah, those are our limb darkening coefficients.
Now, so where are we going now? Figure 3?
Yeah, down just a bit. So there's the observing part of the observing log. That's
The observing
only
log,
interesting if you're interested in a specific star.
figure 3. Ooh, beautiful. Beautiful.
Okay, yeah. So here's the money shot. It doesn't look like much. I think this is beautiful, but it sort of takes an interferometrist to love this sort of picture here.
Nice.
So on the y-axis, we have calibrated visibility squared. You can see the data points are indicated with the black little circles, and the arrow bars are included. And the red line is the uniform, or is the linear, is the angular diameter fit. It's actually the limb darkened angular fit. But in these plots, it wouldn't show very different. So visibility goes from 1, which is essentially where a star is completely unresolved. The most you can say about it is that, look, we observed it.
Yeah, it's there.
Yeah, it appears to be there.
Yes.
down to 0. So this is like normalized visibility. And so it goes down to 0. And at 0, the signal becomes very hard to measure. You know, the signal at 0 is hard.
Yes.
But that tells you a lot about how big the star is, exactly where that visibility curve, hits that 0 line. And so we measure the angular diameters. There are 145 of these plots in this paper alone. If you want to look at visibility diagrams, please go look at all of these, and you'll see some are beautiful. Some are not so great. Some have visibilities pretty high up. Some have all the way down. It's kind of like people, I was at a conference once that, I wish I could remember her name. It was a Cool Stars conference years ago.
Okay.
And the woman presenting said that taking one measurement of a star and saying all stars are like that is like taking a photograph of one person and saying all people are like that. And it's absolutely true. So these are individuals, and they all have their quirks.
That's right. And they all deserve to be shown.
That's right. They all deserve to be studied.
Very
So once we have the angular diameter, we can figure out how far away that star is from parallax measurements. And thank goodness for Gaia.
Absolutely. Yes.
The Parcos was great, but Gaia is just beautiful. And so we know how big it looks to us. We know how far away it is. We can now get the physical size of the star.
Yes.
How many solar radii is it? And that's a pretty simple equation. I don't even think I put it in here.
That's pretty straightforward.
Yeah. And to get the effective temperature, if you scroll up a little bit, there's another simple equation. Again, I do simple equations. Yeah, there it is. Or you can relate bolometric flux, which you can get from SED fits, spectral energy distribution fits, or information in the literature. People have measured these. And your limb darkened angular diameter measurement, and you step on Boltzmann constant, and you can solve for effective temperature.
Very cool.
So now we have the temperature of these stars as well.
Nice. So we got R and T. We're doing good.
That's right. That's right. Those are 2 really good things to start with.
And very good things to start with.
Yeah. So in section 5 here, we have our notes on individual stars, and do not fret. I'm not going to go through all of these because it would take forever.
Take a while.
But there's some really, really good stuff in here. That, some complicated targets, like this first one, just H envelope, reflecting H alpha envelope, reflecting nebula. It's got multiplicity. It's got varying variability. It's just good stuff. And some of these stars have been very well studied.
Yeah, right.
Some of them have been hardly studied at all, and that's always kind of fun. And I got the reference from 1867 in there.
Oh, very good.
Right at the bottom of the page.
Very good.
Yeah.
Secchi, awesome.
Yeah, I couldn't read the paper because I think it's in German, maybe. But I got the gist of it from the other references.
It's always good to cite literature like that. Very good.
Yeah, I was like, good one. So these stars have been studied for a long time. Some of them. There's variable stars in there. There's a lithium-rich giant star, which is really rare. Cepheid variable.
Yep.
So that one's the lithium-rich. Polaris.
We
got. Yep. Yeah, we have Polaris in there. We have a Hyades giant. A symbiotic system with a white dwarf accreting material from a red giant, so kind of a complicated system. A chemically peculiar giant barium star. Luminous blue variable, otherwise known as Deneb. We've all probably seen that. Yeah, one of the brightest stars in our summer sky. There's an S star. Good stuff. So I always like doing these literature searches when I'm writing these papers. It's like, all right, well, I have the star measured. Let me find out why it's interesting now, because there's almost always something, and even if it's just, okay, it's a normal K star or whatever, that's still cool. I still like that.
Yeah, absolutely.
So I had a lot of fun with this.
What
you will, it does help. So you'll see in this list and at this table that's actually showing here, A lot of these stars are in binary systems, and this is information from the Washington Double Star Catalog, and it's another awesome reference. I live on their website.
Yep.
Because they have information about when these stars were observed, what the measurements were. They have individual notes on them, like the reliability sometimes, or yeah, somebody said this, but we haven't seen it since. So it's a great resource.
Nice.
And most of these targets, yeah, they might have a binary companion, but it's either too far away or it's far too faint.
To resolve.
Yeah, that's right. To show up in the interferometric data. So, so if it needs discussion, you'll see the Y in that table. I'm pointing to my screen like that's going to help anybody.
It needs discussion. I don't know if it was discussing about what, but it needs a discussion.
Yeah, that's right. So it's sort of
discussed
here,
right? I mean,
That's right.
So, yeah, very cool.
Yeah. So those were, if you ever run across a paper by Griffith, just read it. There's a footnote in here about a wonderful discussion that he gave about an alternative classification, spectral classification system. You just never know what you're going to find in these papers. Yeah, so just shout out to those. Yeah, as you can see the footnote there. So anyway.
Oh, here we go. Here we
Details.
go. I love this. Okay, I'm going to check it out. I'm going to check that one out. Very good.
I wasn't sure that would make it through the referee process.
I learned something. This is awesome. This is great. This is fantastic. Okay.
Okay. Yeah. So we can go down to figure 4. It's a pretty simple table, but what it shows is the percent uncertainty in the number of stars that we have. Okay. And we want 2% or less on the angular diameter measurement. Okay. Because when it gets beyond that, errors start to compound very quickly. Yeah. Especially when you're doing things like looking at a star that has a transiting planet. Yep. And now you're thinking about like size and density. The radius really matters. Yes. So you want as small of an error as you can get. Yes. So we have, again, 145 diameter measurements. Awesome. We have them. They range from 0.1% to 46%. With an average of 1.8%. And you can see that most of the stars, a good majority of the stars, are in that 0 to 1 or 1 to 2%. Yep. Oh, yep. Lawnmower. I hope you guys can't hear that through my.
Oh, it's okay. Okay. I enjoy the smell of green grass through the internet.
I do too. Yeah. And I wouldn't want to be out there. It's too hot. But anyway. And we do have a handful of stars that have the higher errors, 10% or higher, but those tend to be the small ones. So we always take that with a grain of salt anyway.
But no, but this is great. It gives you a sense of the distribution. So
that's great. Cool. So also when looking through this as a sample, found that there were a few kind of interesting subsamples in there. There were targets that were on the list for the Habitable World Observatory, HWO. And that's a mission that's being planned. It'll be an IR, optical, and UV, and it's going to search for signs of life on exoplanets. Yes. And what the mission star list has been published that says, these are the stars that we're most interested in. Please observe these.
There you go.
Right. And some of them have already been observed. So we need to characterize them as much as possible, not just for target selection, but also for like mission planning. So if you like observing stars and you like measuring stars, definitely check out the mission star list. It's nicely written. It's got great tables of stars of interest. And that might be a focus to say, oh, okay, these are cool to look at.
Particularly ones with a large, between it's 27%.
Yeah, some agree and some do not. And
some need a little more looking at.
That's right, and we would like to know why.
Indeed.
Yeah. Another sort of subcategory were stellar oscillators or astroseismic targets. Yep. What's nice about these is you have the diameter, the radius from interferometry. You can get the maximum frequency from the oscillation studies, and then you can directly get the mass of the star without stellar models. Yep. And that's the only way that you can do that without, it being in a binary system. So it's a really cool technique for getting
everything
stellar masses.
So very good, and that gives those very cool. Good.
Yep. And sort of the last subcategory are these things called zero crossers. So you can go down to the final figure.
Yes. What is a zero crosser?
I know, this is beautiful. Oh gosh, I could just sit here and admire this all day. So again, we have spatial frequency on the x-axis. Oh, and I should have mentioned earlier, spatial frequency combines baseline and wavelength, because we have a lot of baselines and we have a lot of wavelengths.
Ah, yeah, yeah,
You
yeah.
combine them into one, because otherwise the plotting would just be
I'm with you. Yes,
tedious.
I'm with you.
And calibrated visibilities on the y-axis here.
Hmm.
And you can see how this has data all the way down the first lobe. It goes through the first null, so sort of towards the zero, and then it comes up on the second lobe like that.
Yep, that's
When
beautiful.
it comes to angular diameters, that's the primary fit of the first lobe. That's where the angular diameter shows up.
Hmm.
Things like gravity darkening and limb darkening show up more on the second, third, fourth,
It
fifth,
does.
sixth
It
lobes. Um,
very
we
cool.
don't have particularly long baselines. So there are other interferometers. VLTI, CHAR have gotten
For example,
beautiful data. Just whoop, 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 it just keeps going.
lovely.
Yeah. But we can see the effects of the limb darkening sort of after that first null and onto the second lobe.
Hmm.
And this, I said before, it has to do with the different layers in the star. When you're looking at the center, it's basically infinite optical depth. You can see
Essentially,
all
yes.
of it. And then you go off to the side and you're sort of looking through different temperature
Cool.
gradients. The opacity changes, so it looks a little bit darker. And it is really hard to measure directly. I've mentioned that before. And there's all kinds of different laws out there and power laws and these linear laws that we've been using. And that's actually what I've been working on now is, okay, well, we have the sample of about 100
Oh, yes.
stars with either data to the null or past the first null, or close to it.
Giving you a good
What
handle on that.
laws look best?
Hmm. Hmm.
Um,
Very cool.
so that is what we were doing with this paper. I would like to tell you 3 fascinating things about interferometry before we end. These are my fascinating things about interferometry.
Okay, we got three.
Okay, yeah.
One.
Number 1, it was an idea well ahead of its time. The first star to be measured was in 1921 by
Okay.
Michelson and Pease.
Okay. Yes.
And they put the 100-inch telescope top, they basically put a big strut across it, brought the light in little mirrors, brought it down to the main mirror of the telescope, and then saw where the fringes went away. And that's how they determined the size of Betelgeuse.
Awesome.
Yeah, but it took so many technological advancements to put this into regular use, computer and laser systems and just everything, beam management and software. It's a pretty
Yeah.
complicated system, but they did it so elegantly and so beautifully over 100 years ago. And I love that. I love that. Okay.
That's wonderful.
The second awesome thing is the amazing resolution. It's the best in astronomy. We talked about that.
Woohoo.
And the third is that with all of those complicated systems, including things like weather, if the array is going to be grumpy or not, if the vacuum system is working, if your beams are lined up, if your optics are all happy, it's the most amazing thing that it ever works at
At all.
all. So many things have to go
Oh,
right
yes. Oh,
for it to
yes.
go right.
Absolutely. I understand that very well. Very cool. That is beautiful. Well, thank you for that little bonus extra.
Oh, yeah.
That was great. Very cool. Ellen, I want to thank you so much for walking us through this very awesome article on NPOI vintage. Thank you so much.
Yeah. I appreciate the opportunity. I love talking about this stuff.
Sure. And as long as you say that, I'll go ahead and dig into it a little bit. Since you kind of hit it a couple times, sometimes you sort of, yeah, you hinted at it. And where do you think we go from here, given the published article? Are there, there's probably more in the NPOI archive itself you can
Hmm.
go after? Would maybe some of the new telescopes like Rubin be of interest? And then you tantalizingly left us off at the end there with those measuring limb darkenings past
Yes.
first null, and
Yes.
that sort of dribbled
Hmm.
off into wherever. So,
Yeah.
so where do you think we go? Where do you think we
Well,
go?
right now, yeah, this was sort of global look at the data archive,
Okay.
right? What's in there? What can we sort of get out that would be useful? And there are things I want to look at, like stellar rapid rotators of stars that are rotating so rapidly that they're like oblate.
Yeah,
And
yeah.
if we have the right kind of coverage, we can measure that, the
Hopefully.
difference between, the short axis and the long axis.
Nice, nice.
Like to, yeah, and to look into the limb darkening of these stars and see if there's some that, and it won't be all of them. The data just aren't clean enough for a whole lot of them, but I have a large sample. I'll whittle it down from there, to start to determine more about the limb darkening of these stars. And I've actually been talking to folks at other interferometers about this and sort of comparing wavelengths and stuff. So,
Nice.
collaboration is always the best
Always
part.
a good thing. Yes,
Yeah.
absolutely. Very cool. Well, it'll be really exciting to see that develop over the next couple of years. Be very exciting. So I look forward to it.
Yeah, I do too. Thank you.
All righty. Ellen, thank you so much once again for walking us through your very awesome article. And that will do, everyone. And I hope this made your stellar astronomy day just a little bit better. And we will see you on the next one. Bye bye.